Hi everyone, welcome to the third tutorial on fluid mechanics laboratory. Today I'm going to talk about the second experiment known as Bernoulli's theorem. This experiment or this theorem is also known as energy equation in hydraulics. It's the most important equation. There are three basic equations, right? Equations in hydraulics. First one is the energy equation, right? Energy equation, and this is the energy equation we are going to talk about. Energy equation, and there is another one called momentum and momentum equation, and there is another one. This is the first one, second one, and third one is the most important, continuity equation. Continuity. It is basically this one. Continuity equation. Okay, so we'll see that while calculating different variables from this experiment, right? So since it is an energy equation, we're going to cover this part only. So you know what happens with energy. Energy is the ability to do work, right? It manifests in different forms. For example, it may be in a pressurized form, it may be in potential form, right? And it may be in a kinetic form as well. And there is another form called internal energy. So these are the forms: pressure, elevation, kinetic, and internal form. So what happens with the internal energy? Internal energy is basically due to molecular agitation, right? Due to temperature increase or decrease. So that is related to internal energy. And heat energy, you can subtract to, or you can even add it to the system, heat energy. But what happens with this potential energy and the pressure energy and the kinetic energy? If you just bring, for example, if you store, you have a tall building here, tall building, and then what happens if you just bring one body here? If you store a body with certain mass, right, mass m, and after that it is 10 meter height, and if you just allow it to fall, right, freely, then what happen? It will destroy everything, right, that is located on the ground, because when you are storing this body, it is storing a potential mass. We call it mgh, the mass of the body multiplied by that acceleration due to gravity and how much height, right, you are just putting it there in a vertical direction. And then if you just allow it to fall freely, then it will hit this body. And before hitting this body, what will happen? Because it is starting from the rest and it is hitting this body here with a certain velocity, right, v, then all of its energy, potential energy, will be converted to kinetic energy, and then it will destroy the body, or it will work. Mainly it will do some work, right? That is the kinetic energy. So we'll just resemble these things in a fluid flow. And when water flows, same situation happens. We'll just try to understand that basic theorem, right? And there is another one, pump energy. We use pump to push water, right, at the top of a building to store water in a overhead tank, and we use a pump to distribute water, and even we use overhead tank to distribute water because of the gravity. So we'll understand that basics as well, why we need to understand this energy equation, right? And we'll verify that energy equation as well. So that's why in the year of 1938, Daniel Bernoulli, he stated that if a system is in a steady state condition, right? Steady state condition. What is steady state condition? Steady state condition means if the flow variables like the velocity of flow, the depth of water, and the flow rate Q, these are constant with respect to time, means this won't be changed. This should not be changed. If everything is constant, then what will happen? And the fluid, right? For example, I'm considering here water is flowing through a pipe with a velocity, flow rate Q, this feet cube per second or meter cube per second, whatever the rate is with a velocity v is flowing through this pipe, right? If this v and everything is constant, q constant, then what will happen? Then Bernoulli is stating that at every section, section number 1, section number 2, section number 3, at every section, the total energy will be same or constant. What is the total energy for a fluid flow? So if the condition is steady state, and at the same time there is another assumption that the fluid, the water or any kind of fluid is flowing through a pipe, this should be non-viscous. The non-viscous means viscosity would be 0, right? Means frictionless. It is a kind of ideal. It is ideal fluid. He's talking about ideal fluid. So that's the reason. If the fluid is ideal, and at the same time it should be incompressible. Incompressible means what? Means if you just increase pressure, then the density or the volume of the fluid won't be changed. For example, for gaseous state, if you just increase temperature, then what will happen? The gas molecule will be agitated, and then it will increase in volume. But if you just apply pressure in a gas tank, then it will be reduced in volume. That's why the density will be changed. For this case, the fluid should be incompressible. For water, if you push, it won't be compressed or it won't be expanded. So that's the reason in a steady state situation or in a steady state condition, the total energy at every section of a fluid path of a fluid flow will be same. The summation, he's talking about the summation of elevation energy, summation of pressure energy, and summation of this velocity. So we call it head in terms of energy here in fluid mechanics or in hydraulics. So if we consider that a pipe, it is just locating from this datum. This is our datum, right? Reference. This is a reference level, and we're measuring everything from this reference level. We know that, right? And if we consider this is G1, the elevation, it is at the ground floor, and we have a pipe that is at the first floor, and the pipe is inclined this way. It is G1, and it is G2, it is Z3 at these sections, right? And what will happen according to Bernoulli's theorem? It's talking about that since it is elevated, right, at a certain amount, G1, so there will be elevation energy, elevation height, G1 plus pressure. Since what is flowing through the pipe, there will be some pressure energy. It is called pressure head, right? P, it is called P over gamma. Plus, since the water is flowing with a velocity v, definitely there will be kinetic energy. We call it v squared over twice g, and this amount is constant, right? At every section, section 1, section 2, section 3, everywhere, this will be constant. So why is that? That is the ideal situation, right? When the situation is ideal, then you will have that constant energy. This is called total energy or total head. We call it head. Why we're calling it head? Because it's the unit. See here, the unit, either it's unit of length, either is in feet or in meter. So what about this one? And what about this one? Can we sum different object? Can we sum different, like 4 chair plus 3 tables is equal to what? 7 watt. What will be the unit? That's why you have to sum them up when these objects are same. And if the variables are same, then we can sum them up. Otherwise, there is no point of summation. So let me just show you that if the units are same for all of these 3, right? This one, and this one. So then we can even make a summation, right? So here is you have to understand that we know G is the elevation, or G1 elevation, it's either in meter or in feet. So what about P over gamma? P is the atmospheric pressure, you know, pressure means pressure, right? Pressure means what? It is, what do we do? Force, right? Force per unit area. That means force is Newton and it's meter square. So Newton over meter square, right? And then what will happen about the gamma? Gamma is the unit weight, right? We know gamma is equal to rho g. And the unit weight of gamma, we know 9.81 kilonewton per meter cube, or it is 981 Newton. Whatever the value is, not a problem, but we are talking about this unit only. So that meter cube, the Newton per meter square and meter cube over n. So what will happen? This will be neutralized and we'll have m. So this is basically another unit of length, right? So this is that. And we also have velocity, right? V squared over twice g. So we know velocity is meter per second. It will be squared, and then 2 is only number. We don't have any unit. And g, we know that g means meter per second squared. So what will happen? Meter square over second square, and if I just reverse it, second square over meter, second square and meter square and meter, it will be meter, right? So we all have the unit of length, so we can sum them up. So that's the thing, we're summing different forms. You may be surprised that, okay, why we are summing this together and what is actually happening there. So that is the Bernoulli's theorem. If the fluid is in a steady state condition, and if the fluid we consider as non-viscous and incompressible, then the total energy or the total head or the summation of elevation head, and this is called pressure head, and the velocity head will be constant, right? So that's why he's doing this one, and it will be continued. So today we'll verify if this is the constant or not, if the theory is okay or not. We'll test that using our experimental setup, whatever we have, we'll test that. That's why we're calling this experiment as Bernoulli's theorem. This is the Bernoulli's theorem. So let me just show you quickly that experimental setup, and we'll go to the calculation part. So here is the experimental setup. It is as before. It will be inside, right? You'll see a setup like that, but in reality, you'll see the setup like this, right? You can't even, so we have a section here at the bottom, this glass, and you can see what is actually happening. So inside that, the section, and we have, see, it is like this. That section is this one. It is changing. The section is changing. What is flowing from left to right? We have a section here, then it is reducing here, and then it is again increasing the section. And what is happening? We are just inserting some pipes, right? These are capillary pipes. We call it piezometer. So these pipes are narrow in diameter. So then what will happen if water flows from left to right through this pipe with variable sections? Then we inserted this pipe right here, here, here. When the sections are changing, then water will rise inside that pipe or small diameter tubes. We call it piezometer. So this tube will measure the pressure head, P over gamma. So the height of water inside that piezometer will give us the pressure head for that location. If the pipe is here, if you want to measure pressure here, right here, you have to see what is the height of the water inside that tube, capillary tube or piezometer. Then we'll see, we can measure that, okay, it is the pressure head at this location. So what will actually happening? Why we are changing the diameter here? Only to test if the Bernoulli's principle is valid or not. Because if I want to show you the complete equation here, this is the pipe, water is flowing with a velocity v in general, section 1, and this is the section 2, and it is the datum, right? We're measuring this from, this is G1, the bottom is located up to here, the center, okay? The center is up to G1, and here it is G2, or you can even consider this one, whatever it is not a problem. And then we'll have what? Pressure head. If we insert this type of tube, right, here, and that type of tube here, water will be here, and for this case water will be here. So that is the pressure head. We can say this is P1 over gamma, and that will be P2 over gamma. Since water is flowing with a velocity v, and velocity also, the velocity would be different, it is v2 we are considering, and v1 is here, then if we just calculate v square over twice g for this part and this part, we have to add some amount of energy here. So that will be v1 square over twice g, and here it will be v2 square over twice g, this amount. It is not the tube, it is the energy line. Then if we add this, see, if we insert even multiple points, we can see we'll have another location. If we add this physiometric level, then we'll have a line. This line, we call it hydraulic grade line, HGL. And if we add all this together, and we are getting this v square, right, divided by twice g, and if we add even, we'll have this part as well here. If we add this line, we'll get EGL, energy grade line. So the line connecting the total head is called the energy grade line, and the summation of elevation head plus the pressure head is called the energy grade line. If we just connect all this piezometric level, we'll get the hydraulic grade line, this one. So we're just applying the Bernoulli's principle in between these two sections, because at every section it will be constant, so we can easily apply this equation for these two sections. How can we apply that? So it will be like this one, G1 plus P1 over gamma plus V1 squared over twice G is equal to Z2 plus P2 over gamma, because gamma is constant, is the unit weight of water. Since it is the same water, we're not changing. Water is not changing in density and everything within this section. We're considering that, and it is not possible to change if we don't change any other condition as well. So now it's V2 square, right? V2 square divided by twice G. So this is the Bernoulli's equation for two sections, right? Considering that the fluid is non-viscous, it is incompressible, and at the same time it should be what? In a steady state condition, right? But in reality, what will happen if flow, right, if water flows through a pipe, then the pipe surface is not smooth enough to, right, it's not ideally smooth. There will be some roughness, right? Every surface in this real world situation has some kind of roughness. That's why there will be some friction loss. So in reality, there will be some friction loss, and the water is not even non-viscous. It is, of course, it has viscosity, because viscosity is related to temperature. If we increase and decrease temperature, the viscosity will be also changed. So then what will happen? In reality, this equation is not valid. So for writing this equation, because when water is flowing from this section to this section, and it is just passing a length, and in between these two lengths, the velocity won't be same. The velocity will be reduced. The pressure will be different. So if we sum them up, then what will happen? This equation won't be equal. Then we have to add another term, HL. This is called head loss, right? This head loss term, because we are losing this head or energy. So if we add this head loss at section 2, that is happening in between these two sections, then we can write, okay, now these two terms are equal. Then we can say this is the equation for real world case. If you want to modify the theoretical equation of Bernoulli, then you have to add this head loss. So today we'll calculate this head loss, and we'll see how it varies with different conditions, right? If we change the flow rate, we'll have different values of head loss, and we'll see that how head loss varies with changing velocity and changing section. Okay, now let me quickly show you that what will happen, why these three terms are constant, should be constant, right? So what will happen if we have a pipe here, the diameter is this, and now it is changing its diameter, it is narrowing down this way, the diameter is different. However, we have the same flow, Q in and Q out. We have section 1 here, section 2 there, 1 and 2. We have the same flow rate, Q. So then the velocity will be different, right? We'll have V1 here and we'll have V2. So what will happen to the pressure if we insert another piezometer here and the piezometer here? So what will happen? Because according to this continuity equation, we know that Q is equal to A and V. If you multiply the cross-sectional area, if you know the diameter of the pipe D1 here, you can easily calculate, right? A1 is equal to pi over 4 D1 square. That is the diameter, because here is the cross-section circular. So that is the continuity equation AV. So if we consider Q is constant everywhere, Q is constant, Q, right? So Q is constant. Then what will be V? V will be Q over A. Q is constant, so V1 will be Q over A1 and V2 will be Q over A2. Since the diameter is higher here, the higher at section 1, the area will be higher, right? A1 is greater than A2 if we consider we have A2 here. Then what will happen? Definitely V2 will be greater than V1. If V2 is greater than V1, then definitely V1 square divided by twice G, right? It is less than, means V2 square twice G, this will be greater than this one. So in order to make the equation constant, we have to consider that which thing will be changed to make it constant, because we have G1 won't be changed because of this flow rate or cross-sectional area. We have a P1 over gamma plus V1 squared divided by twice G, right? So if this is increasing, so this should be, it must be decreased, right, in order to make the whole summation constant. So that's why the pressure head will be increased here. However, the velocity head will be decreased, but at this location, the velocity head will increase. However, the pressure head will be decreased, right? Pressure head will decrease as well. So that's the condition. In order to make the summation constant, if the cross section changes, this term velocity head will be converted to pressure head at some point, and pressure head will be converted to velocity head. So what is happening here when water is flowing from larger section to smaller section? Then we have higher pressure head. So pressure head will be converted to velocity head because we'll have higher velocity here. If the section is narrow and we are having the same flow rate, so water has to flow, right, faster. So that's why the velocity will increase, and when the velocity will be increased, the velocity head V square over twice G has to be increased, right? So that is the condition. So keeping that in mind, we'll calculate. So let's move to the experimental setup. So that's why I'm going to show you this one, this setup. Water is flowing from left to right. From left to right, we have a distribution system, and we have this section. We have a narrow section here. We have wider section here, wider diameter. It's called now Bernoulli meter. We'll see in the next now experiment, Bernoulli meter. Then we'll calculate everything. So basically, what is the application? What is the application of this Bernoulli's principle? If you want to design a flow measuring device means you want to measure flow through a channel, flow through a pipe, flow through any conduit, then you need a device that can measure the flow, right? So how can you measure that? You need to apply any kind of hydraulics. So this energy equation is useful, right, to design a system that measures the flow. So in order to design or develop any flow measuring device, we need this. So that is the practical application, right? And there are many other practical applications, and we can see, right, time to time in this experiment, we'll see that. So the main, and we also, yeah, in order to design any cross section, right, of a river, if you want to see what will happen. So this way we'll apply the Bernoulli equation at every section of a river, a channel, or pipe. In order to design the pipe network, we need to know the head loss, and how can we calculate that head loss. There's other equation as well to calculate the head loss for pipe or pipe network called Darcy-Weisbach equation. So that's another history, but for the time being, we'll also apply this energy equation that is called Bernoulli's equation, right? For example, if you want to design any water distribution system, right, it is a overhead tank. The height is that you have a big tank. We saw that in a city, then it is like a 60-meter height. Then you are planning to distribute water at a distance 20 kilometers, right? And if you don't have any idea about the head loss, you're considering, okay, I have the head 60 meters here at the distribution system, and at the household that is located at 20 kilometers from that distribution system, and I'm expecting the same head. So it won't be possible. You have to calculate, right? You have to be able to calculate, because you are just carrying water through concrete pipe or plastic pipe or even cast iron pipe. So what will happen? The pipe will have some degree of roughness. Definitely there will be head loss. So you have to be able to calculate that head loss using this Bernoulli's equation or some other equation. Then you have to apply that head loss here at the distribution system in order to get the same pressure and same amount of flow there at the household. So that's the most practical application. Without, if you just make mistake, right, in your calculation, then definitely there will be problem. And we see some problem in reality. So that's why we have to make sure that we are able to calculate the head loss. If you understand the problem, understand the theory, and you can match this theory to the real world scenario, and what are the factors that may affect, right? So we can remove that, and we can even design a system that is sound and stable. That is possible, right? So that's the experimental setup. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 tubes inserted, right, at the top of the bearing cross section. The tube is like this. And what we will measure, so we're expecting from the theory that here the section, this section is bigger than this section. So in this tube, water will be here. And since the section is decreasing, flow velocity will increase. However, the P by gamma, right, P by gamma, this will be decreased. And again, it is increasing, it will be like this. So if we plot, it will be like this. And we'll see the plot. We'll check if it is like this. And if you plot the velocity, see velocity is here, for example, velocity is here, and velocity will increase, right? Velocity will increase, and when the section is minimum, then it will be maximum, and then it will also decrease as the section cross-sectional area increases. So these pipes or these tubes, these are located at 1 inch, right? The distance are given here, 1 inch center to center and 2.54 centimeter. 1 inch is equal to 2.54 centimeter. And at every section, see here, and at every section where the piezometer are inserted, we have the cross-sectional area. So here at the beginning, we have 1 inch square, and then we have 0.85, 55, 37. These are the cross-sectional area, right? If you see the section, it is this. This is how it's changing its section. So we'll apply our Bernoulli's principle everywhere, and we'll check if the pressure head is showing like this, if the velocity here is showing like this, because it is expected from the theory. in order to keep the total energy constant. And we'll also consider calculate how much head loss we'll have in between these two sections, right? We're considering this section 1 and the end section. In between first and second, we'll have the total head loss, how much head loss we have, because the length is not that it is a few centimeter, right? 9 or 10 centimeters, so 9 or 10 inch. So in between this length, we'll have very small amount of head loss. However, we will have idea how to calculate the head loss, right? Using Bernoulli's theorem, we'll have this. So that is the experimental setup. And see, basically what we'll do here, we have a water distribution system that is a circulating. We are flowing, we have a pump system, then we are flowing water from left to right, and we are collecting this water. We have a collection tank here because water is falling here. We have a collection tank. We'll collect water when it is 10 centimeter depth. We'll allow this system, we'll remove every bubbles, right? We have a setup, we'll remove bubbles. Because see, if you see the real, we have a screw here. If we just turn it on, means if you just rotate it anti-clockwise, then we'll remove the bubbles, air bubbles. At first, we'll allow the system to flow for some time, and we'll remove this, release that air. So our system will be there will be no bubbles, right? Air bubbles. So system is now stable, right? Water is flowing from left to right and flowing through this pipe to, it is releasing this way. And then we'll see we have this head, right, watermark here. Since we have a scale already there, we can easily measure, okay, this is the reading. So these readings are basically P over gamma for each of this tube that is representing that section of the pipe or that section of the tube, right there. So we have the data sheet, we'll put it there, and we are collecting, right? We have a certain section of this tank. We know the section of this tank, then we know the area, and if you know the height, 10 centimeter or whatever the amount is, that will give us the volume of water and how much time it will take to store this 10 centimeter of water. Then we'll have our flow rate P over T. We'll see the calculation, all this thing, right? So that is the experimental setup. We'll collect water and we'll also measure this P over gamma from this experiment. And then since we'll know the flow rate Q, and from Q, we'll calculate V1, V2, V3, V4 up to V9, right, at every section of the channel. Then we'll calculate V1 square over twice G and everything up to V9 square over twice G. Then we'll sum them up. Then we'll calculate total head and head loss as well. We'll see that in the calculation section, right? Since this system, see, before that, as before every time, we have to make this system leveled. If the setup is leveled, then we don't need to measure G1, G2, because if it is leveled perfectly, then if you measure anything from here to here, this G1 and G2 will be same. So we don't need to use G1 and G2 if it is perfectly leveled. If it is inclined, then you have to add that difference, level difference, the elevation difference as well. So we'll store all these values. So that are the details, right? So let me just show you what are the main objectives of this experiment. And you can see these are the objectives, right? To plot the static head means this is the static head P over gamma. That's what I said. It will be looking like this. We're expecting this, and from the experiment, if we see that same shape, then we're done with that. And static head and velocity head and total head against the length of the passes, right, in one plain graph paper. So you have to plot like you have one graph paper length. So we have the length, right? We know the length starting from 0, and this is 1 inch, another 1 inch, 2 inch, 3. This is how we'll calculate the length, and then we'll plot. And then the second one is to plot the total head loss HL against the inlet kinetic head V square over twice G for different inflow conditions. So what I have seen here, I just mentioned when the Q is constant, we'll do all these calculations. If I change the Q, then we'll have different values of P1, P2, right? P1 over gamma, P2 over gamma, everything will be changed, and we'll have different velocities, we'll have different head loss. So we'll change the condition, means change the Q 5 times, we'll collect this water 5 times, we'll measure the time 5 times, then we'll fill up a data sheet and we'll repeat all these calculations 5 times. Then we'll have enough information to plot, to check when the conditions are changing, then what is happening to the head loss. We'll check that. What is the relationship in between this velocity head? If the velocity head increases, then what will happen to the head loss? So we have to know the information, and based on the information, we can design a system, right, that is stable, that is suitable for a practical application. Otherwise, if we don't know the information, then we'll increase the velocity head, right, up to infinity. Then what will happen to the system? What will happen to the head loss? Because our main objective will be to reduce the head loss, but to increase the water flow and to increase the head. However, to reduce the head loss and increase the head it's opposite problems. We have to minimize that, and we have to optimize that issues, right? And here's the questions. So some questions we can do. So what are the assumptions underlying the Bernoulli's energy equation? I already mentioned that one. The flow should be in a steady state condition, means the flow rate for any setup, flow rate, velocity, everything will be constant with respect to time. If it is with respect to time, then it is called steady state. And if it is constant with respect to any length, then it is called different one, right? We'll see that in open channel flow, it is uniform, non-uniform case. And then these are the assumption, and the fluid should be non-viscous, means there will be, we're considering that okay, surface is fluid is also non-viscous, there won't be any viscosity, and there won't be any roughness or any friction in between the fluid particle and the surface, right, of the pipe, the internal surface of the pipe or any surface of a channel. So that are the assumptions. So do you need any modification of equation number 1 when the frictional head loss is to be considered and the conduit is not horizontal? Yeah, definitely we need to use, we already added that one, right? If we have this equation like g1 over plus v1 squared twice g plus, I'm writing in a different order, no problem. And then we need that one, g2 v2 squared over twice g plus v2 gamma. We need this term hl, we have to add this. If the system is perfectly horizontal, whatever it is, we need that. If the pipe is perfectly horizontal, no problem. We have to add this head loss because we're having head loss because of the frictional effect. And another one, this is A, another one, if it is inclined, right? If it is, the system is inclined this way, water is flowing through this pipe and the pipe is inclined. So if we just measure, so we have to add this term, delta G, right? Head loss plus we have to add that delta G at the end. So these are the modification we need. So when we'll apply this for real world case, and I'll show you what are the applications, and you can understand this one. These are the modification I need. And what are the difference between the energy grade line and the energy grade line? So that's the, I already mentioned that one, right? If we consider the total head loss, that will be energy grade line. And if we consider only the pressure head, the piezometric level, right? So that will be the hydraulic grade line or energy line, right? What will be here? Here, if we add this, these are P1 over gamma. This is P2 over gamma. This is called HGL, hydraulic grade line. And if we add velocity head, here, V1 square over twice G, and here, V2 square over twice G. So that line is energy grade line. This is hydraulic grade line. This is energy grade line. Okay. For open channel flow, the surface of the water is the hydraulic grade line, but since it is a pipe, the flow is pressurized flow. So what is the difference between open channel flow and the pipe flow? When the surface of the water is open to atmosphere, like any river flow or any channel flow that is open to atmosphere, then the flow is called open channel flow. However, if the flow is happening, right, it's occurring through a pipe which is through a certain diameter of pipe, and there is no atmospheric pressure inside that pipe. Rather than the pressure we have, it is a gauge pressure, we call it a pipe flow. And pipe flow may also be if flow, right? Water flows through pipe, and if the pipe is not full, like water is not flowing full, so then this will be also open channel flow, even though it is flowing through a pipe, right? It doesn't mean that, okay, always if we have flow through a pipe, it will be pipe flow. For water distribution system, maybe it will be pipe flow because the flow is pressurized flow. However, for Swiss network, we have a flow that is half full, so then it will be open channel flow. That's why we have to check the system, and we have different hydraulics, different calculations, different equations for dealing with all these conditions, open channel flow and pipe flow as well. So let me just quickly solve the fourth example. See, it is a vertical pipe 3 feet in diameter and 60 feet long, has a pressure head at the upper end of, right, 18 feet of water. And when the flow of water through it is such that the mean velocity is 15 fps, feet per second, the frictional loss is head loss is HL is equal to 4 feet from the pressure head at the lower end of the pipe when the flow is downward and upward direction. What it is actually trying to say here, if I quickly draw so that I can understand. So that is the pipe with a diameter 3. The diameter of the pipe is 3 feet, and the length of the pipe is 60 feet here, and it is the ground here. We can consider it's the ground. Water is flowing. Water may flow either in a downward direction or upward direction, and they're also mentioning that here it is located at 60 feet, right? For example, it's at the top of a building, 60 feet, and we have the head, total head H is equal to what? Total head, this is basically elevation head. It is 18 feet, okay? Water head is 18 feet. It's there. And then the velocity, right? The V is equal to 15 feet per second. And in between these two sections, whether the flow is moving upward or downward, it doesn't matter. HL is equal to 4 feet. So they're asking, okay, what will be the pressure here when the flow is moving up and it is flowing downward? So they're asking what will be the P by gamma value. So at first, okay, we're considering flow is downward, A. Flow is downward, water is flowing downward. So we're applying so when water is flowing in a downward direction, then we're considering this section 1 and that is section 2. We're applying the Bernoulli's principle in between these two sections. The pipe is perfectly vertical. So at section 1, we'll have some, okay, we can write the generalized equation G1 and then P1 over gamma plus V1 square twice G is equal to G2 plus P2 by gamma plus V2 square divided by twice G plus HL, right? So what is the G1 for section 1? We know it is 60, right? Plus P1 over gamma. They already mentioned it is the pressure head. They already mentioned here the pressure head at the upper end is 18 feet of water, so it will be 18. And what is the velocity? It is 15 squared divided by 2 into G. G means 32.2 for FPS system. G is not 9.81. It is 32.2 equal to, for this one, we're measuring from this one, right? This level. So G2 is 0 plus we have to measure that P2 over gamma plus what will be the V2 squared, same value, right? 15 squared twice G into 32.2 plus what is the head loss? 4. So these are same, right? These are same, so we can neutralize this one. So this is a 78 minus 4. If we just bring 4 from right to left, so what we have, this is our unknown, right? So that's the value, 74 feet. 74 feet, the pressure head will be 74 feet here if the flow, right, is downward. Then what will happen if the flow is upward? Now we're considering second form. When the flow is upward, the equation is same. The flow is, now the flow is upward, okay? Now flow is upward. So this section is 1 and that section is 2. Flow is upward. This section is 1, that section is 2. So this one G1. So we are here. For G1 it is 0. We have to calculate P1 over gamma when the flow is upward, because this is 1 now. And V1 is same. We can cancel this out because it is 15 for both. We just cancel it as before, right? So equal to G2. Now we have G2 here. There's section 2. It is 18, not 18, it is 60. And what is the P2? It is 18. Plus what is the head loss? It is 4. So what will be the pressure head at section 2 when flow is upward, right? So that is the 78 and 82, okay? That will be 82 feet. So here the head loss is 82 feet when the flow is moving upward directions. This is how we can solve this equation and we can apply this Bernoulli's equation. This is one of the practical example of Bernoulli's theorem, okay? So let me just show you quickly the sample calculations. Here at the data sheet, you can, what type of measure we need. So the bold, right? These are the measure data, and the empty or blank, we need to fill this up. So here the tank, a measuring tank, where we are collecting water. So this tank I just mentioned here, this water collection tank, the size of this tank is that one, 30.5 into 45, and we are storing water up to 10 centimeter. We're calculating the volume. So here it is. So that is 45 centimeter into 30.5 centimeter, right? That is the cross-sectional size. And initial point gauge reading, because when I'm measuring this tank water, so at the beginning it is 0 and the final one is 10. So we have total 10 centimeter of water. So that's why it's 0 and 10. We have 10 centimeter height of water. And for storing water for 10 centimeter depth inside that tank, we spent this time in 98 seconds. It took 98 seconds. So what will be the volume of water? V. The volume of water is the area multiplied by the depth, right? So it will be 45 into 30.5 into 10. It is going to be 13. Okay, it is 13,725 this centimeter cube. And what is the Q? We know Q is equal to V over T, right? If we divide this volume divided by T, volume by time in second, so we have 140.05 centimeter cube per second. So that is the flow rate. For group number 1 or for condition number 1, we have this flow rate Q as 140.5. Now we are just see cross-sectional area. It's already given there from this data sheet or from this experiment. We have cross-sectional area in inch. We're just converting this cross-sectional area as centimeter squared, because we know 1 inch is equal to 2.54. If we multiply 2.54 into 2.54, because it is area, then we are getting 6.45 this one. Then 0.85 we are multiplying and which calculating from, okay, these are given data. We are measuring this one, we're taking this reading, that's why it is in bold. So we have this. So we have the flow rate Q. Now we need to calculate the velocity for each of these 9 locations, right? When we're moving from left to right. So we have Q and we have the cross-sectional area, right? So we can measure, because we know the continuity equation. Q is equal to AV. We need V Q over A, right? So V1, V2, V3 up to V9. So you know the Q 140. So the V1 will be 140.05 divided by 6.45. 140.05 divided by 6, it is 6.45. It is giving us that 21.71. And for section 2, if you just divide the same thing, you'll get, you have to repeat all these calculations, okay? So we can do that. And then we have to calculate that velocity head. So if you just, for each of this segment, each of this section, right? So then if you just square that velocity head, it is 21.71. If we square it, if you divide it by 2g, 2, and divided by g, since we are calculating centimeter, so g is 9.81 meter per second, so it is 981 centimeter per second square. Okay, 981. So it is 0.24. Yeah, it's there, 0.24. And then we're see this reading P over gamma for each of this section. We're getting from that reading. We're directly reading from here. We have the setup. We're taking reading from this scale. We have the scale. We'll see the watermark here. Then we'll definitely take a reading from this. So that's why it is in bold. We'll take the reading. So these are the reading we got it from the experiment. Okay. And then what we are trying to do here, total energy here, see the summation of all two, because we are not considering the elevation head, the system is perfectly level, that will be neutralized, so that's why we don't need to do that. So it is the summation of these two, right? V square over twice g and 21.3, so 0.24 plus 21.3, right? 0.24 plus 21.3 is giving us that much, 21.54. These are all in centimeter. So we are getting this one, and we have to do the same for all of this. Once we have this for section number 1 and section number 2, right? If we just make a difference, we take a difference in between the first section and the last one, then we'll get the head loss HL, right? Head loss HL. So what will be the head loss HL? It will be that 21.54 minus 20.74, right? 20.74. We're getting 0.8 centimeters. So in between that 10-inch length, or 30 centimeter length, we have the head loss 0.8 centimeter, right? So that is the calculation we are getting from here. So we are calculating the head loss for this group 0.8. So that is the group number 4. We did the calculation for this one. So then we change the condition Q, and we also have done all this thing repeatedly, and we are calculating this one. We are changing the Q again. We're getting this value of head loss, and since we need to see the change of head loss with velocity head, so we have 5 different flow rate, 5 different head loss for 5 different groups, right? We're sharing this information here. Now, according to that objective, we are gonna see the graphical plots, right? That's why the objective is this. We have to plot that static head, velocity head, and total head against the length of the passes, and then have to plot the total head loss that is just calculated here, HL, and against the inlet kinetic energy, right? So that's why we'll see. We have the blank graph paper, but let me show you the graphs. So these are the steps we have to do. I'm going to show you how to, if you just calculate everything, and then you can have a blank graph paper, you can plot that, or we can easily plot that using Excel sheet. Let me show you that in Excel sheet. Okay, it's pretty simple. It is not that hard. We can easily do that. It's not that difficult to do. Okay, I'm doing that pretty quickly. Let me just quickly switch to the computer I have, and here is the, so it's pretty simple. You can calculate this way. So these are the Bernoulli's principle we are verifying. We're verifying if the total energy at every section is constant or not, and how much head loss we have in between 2 sections, and and how it varies with the length or with the velocity head. If you increase the velocity, what will be the head loss? That's why we're checking for different flow conditions, because for different flow conditions, we have different inlet velocity head. So let me just quickly share my screen right now and show you the graphs. The first one is asking, okay, it is this one. So we are putting velocity head along x-axis for 5 groups. So here is the velocity head, and here is the head loss HL for each of this group. Okay, we're putting in a vertical, and then we are selecting these two, right? We know, I think, how to plot. You can select this and then go insert, right? And you can insert that type, what type of thing you need to insert. You can do that, right? Here, if you insert, it will give you this, but we are plotting this one. Since it is this point are not located in a single line, that is the reality, then what do you have to do? You have to add a line, that is average line. So how can you do that? You can insert a shape, this shape, and from this one, just considering that, okay, this is my average line, that is putting some point on the left side and some point on the right, points on the right side, this one. That is using your eyeball, using your judgment, using your estimation of average line, right? So this is how we can plot this one. So what we are basically observing here, what is our main take-home message? See, this is the velocity head. So velocity head is increasing if you go from left to right. Means if you change your flow rate, velocity head is also increasing. So then what is happening to the head loss? Well, that is the main point we need to know. Head loss is also increasing. So that means you can't even increase your velocity, or you can't even increase your flow rate for a certain diameter of a pipe, right, to get more flow. No, it's not possible. Then your head loss will be more. The head loss is also increasing. So in order to reduce the head loss, we have to increase the pipe diameter, right? And we have to use a pipe that has a smoother surface. And what is the other objective? We are going to plot, right, the velocity head, that is the kinetic head, v square over twice g. We just copied from that data sheet. And the length of the passes, we have 1, 2, 3, these are in inch. I converted it to centimeter here. So I'm plotting all these three, right, together here. So I just selected this, and then I just inserted this way, the same, inserted this way. It is that plot, okay, that plot. So which one is for which? If I select this one, see, that one, that should be velocity, right? This should be velocity. You saw that. See, this is the velocity head. When the section is narrow in the middle of the passes, we have this higher velocity, and at the beginning and at the end, section is wider, we have less velocity. So velocity head is also lower. And what is this one? This should be pressure head, P by gamma, right? We saw that from the experiment. This was expected, P by gamma. So when the section is narrow, velocity is higher, however, the pressure is lower, pressure head is lower. So when you're just summing them together, so that upper line, this one is the summation of these two, right? This line and this line, that is the summation of these two. And you still see it is not, even this point and this point is not same, because we are having some head loss. The difference between this point and this point is giving us that head loss in between these two sections. That's why it is still inclined. That is the summation of these two, velocity head and the pressure head. So these are the main objective of this experiment. And what we have learned today, what is Bernoulli's principle? Bernoulli's principle is nothing but a summation of elevation head, pressure head, and velocity head. If the steady flow is in steady state condition, right, or if the flow is in incompressible state, or if the flow is non-viscous. So that is the condition. And what else we have understood, right? We have idea about how to apply this for real world case, right? In reality, we'll have head loss. So we have to add the head loss term, the head loss term, right? HL at the end. If it is inclined, we have to use that elevation difference, delta G. And we already have idea about how to apply that for a pipe that is vertical and it has a certain amount of velocity. If the flow is flowing in upward or downward direction, we already have, right, solved that equation. We know that how to solve this equation, and we already have idea about how it varies, how the head loss varies with the velocity head. We already saw that if velocity increases, then head loss will also be increased. And we also saw that, okay, verification of Bernoulli's principle, when the section is wider, then your pressure head will be higher than for a section that has lower cross-sectional area, right? And vice versa for a velocity head because of this continuity equation. We know that, right? So these are the calculations, sample calculations, and the plots we need for completing that report. You can go through this because all these calculations I've done based on actual data collected from actual setup of this Bernoulli's theorem experiment. So this is experiment 2. And if you have any hurdle, if you face any hurdle, or if you face any difficulties while calculating, you can practice this one, and yeah, just let me know. And you can ask your instructor as well, because in reality, you have to test the experiment, you have to measure by yourself, and then you will see different types of difficulties, right, you may face. So that's that. I'm gonna finish it right here. And yeah, thank you very much for watching that tutorial series. And I think the next experiment will be experiment 3. It is the Van Jury meter. That is the practical application of this Bernoulli's principle. And after that, we'll also have some other flow measuring device. We'll develop a device and we'll try to calibrate that device so that now we can put this device on the way of a flow, and we'll get the flow measurement, how much water is flowing, right? So that's how we need to know how to calibrate any device and how to apply Bernoulli's theorem to develop or design any flow measuring device. So that will be Van Jury meter. It is already there. And having said that, I'm just finishing here. So thank you very much for watching. Stay safe. See you in the next tutorial.